The second way to increase the area of the TS diagram is to superheat the steam to higher temperature. So let's take a look at this TS diagram. So from the baseline of 1, 2, 3, and 4, if we increase the temperature of steam that exceeds the boiler to 3 prime, then by the amount of the temperature increase, we could increase the area of the TS diagram of the Rankine cycle. Okay, so obviously that would cause the more the investment in terms of the steam generator size and steam generator heat input, but it actually gives us certain payback. Okay? And another advantage of having superheating the steam is that we can also increase the quality at the exit from 4 to 4 prime. And as we discussed in earlier slide, that is good for us. However, there is a limit that we have to consider. We cannot keep increasing this superheated steam temperature up and up, because that temperature is the highest temperature of the steam turbine, and that is limited by the metallurgical condition of blades. Typically, that is limited by around 620 degrees Celsius. So what would happen if we exceed that kind of limit in terms of temperature? Okay, so that is possible damage that we can think of. The high temperature operation can cause thermal fatigue, because now in the material itself there should be a huge thermal expansion. Okay, and this thermal expansion can cause certain cracks or fatigue around your casing or blades of a steam turbine. And if you have cracks or damage around here, as you see, then that could cause big problem in the safe operation of steam turbine. And another possible damage is that high temperature steam can accelerate the corrosion problem. Okay, and sometimes, always steam is not pure, so there are always certain impurities inside the steam, and these impurities can be more easily deposited on the surface on the steam turbine at higher temperature. So by running the steam turbine quite certain time, if you take a look at what happened inside the blades, then you can see certain deposition of impurities inside the steam on the steam blades, and that can degrade the performance of the turbine. Okay, so let's think about the third way to improve the net power output of steam power plant. Okay, so now we talked about the lowering the condensing pressure. Okay, and we also talked about superheating the steam, but this superheating should be limited in terms of temperature to protect the blades of the turbine. So we usually have this kind of limitations as Tmax. Okay. So another possibility is that first, if we increase the pressure of the boiler, okay, from 2 to 2 prime, then we can increase the net work by that amount of area. Okay, but if you compare to 1, 2, 3, and 4, we in return decrease that much of area. So by having gain in terms of the green shaded color by increasing the pressure, we have to sacrifice certain loss of network in the red shaded color. So how can we get both? So the possibility is that what if we increase the pressure and go up to 3 prime, then it goes down, and we have second turbine and reheater, as we discussed earlier for the gas turbine, but same concept can be applied for the steam power plant. So by reheating the steam again back to 3, then letting that steam go through secondary turbine to make 3 to 4 expansion process, then we have entire increase of the area, including the green shaded color and orange shaded color. So that is why why you have to think about reheating and secondary or multi-stage turbine systems even for the Rankine cycle. Okay. Then we have talked about the three possible ways, and yes, we have to consider these all three possible ways into the Rankine cycle to increase the net power. But how about the thermal efficiency? Obviously, by doing those three possible steps to increase the net power, consequently, we also could increase the thermal efficiency. But is there own better way to increase the thermal efficiency? For sure? And what did we do to increase the thermal efficiency for the gas turbine? Do you remember that? Yes, we used the regeneration. So now, can we use the regeneration concept for the Rankine cycle? So what is the concept of the regeneration? So the core motivation of using regeneration is to preheat the working fluid. So by the amount of preheating, we could save the heat input that is needed during this heat input process. So the question is that, can we preheat the water before that water goes back to the boiler or steam generator? Okay. There are two ways to use the regeneration concept for the Rankine cycle, and we call that as feed water heater. So the objective of using regeneration using the feed water heater is to again preheat the working fluid water before it goes to the steam generator, and consequently it will improve the thermal efficiency. So there are two types of feed water heater. One is open feed water heater, and second one is closed feed water heater. Open feed water heater is simple. It's kind of mixing cold water with hot steam to make a warm water. So that is more likely your bathtub. So you mix cold water and hot water to make a good temperature water that you really want to take a bath. Same thing. We take out certain amount of steam in the middle of a turbine and mix this steam with cold water after condenser, and that in the open feed water heater, then these two, steam and water, condensed water, are mixed to make a certain warm water that goes to the boiler. Closed feed water heater is actually the heat exchanger. So now we have heat exchanger and we have steam extracted from the middle of the turbine and goes to 1/9 of the heat exchanger, while another path is going from the condensed water to the boiler. Then steam has hot temperature, and this hot temperature steam can transfer heat to the condensed water, which is cold, to preheat the water. Okay, so there are also different types of closed feed water heater, but I'm going to stop here. But what you have to remember is that yes, we also can use the regeneration concept for the Rankine cycle, and second, there are two types of feed water heater, to make use of the regeneration. One is more like a bathtub mixing. The other one is more likely heat exchanger. In reality, for the usually the steam power plant is really huge, like in terms of size, and it's really, really big. Okay, and we have to make use of all these possible ways to improve the net power output and the thermal efficiency to make a good, vapor power plant. And this is one example of how realistic steam power plant is made of. Okay, we have a big size boiler. Okay, and the boiler, and also we have multi-stage steam turbines, like a high pressure turbine, intermediate pressure turbine, and low pressure turbine. Okay, and also after we have condenser, and there are many regenerators. And because those regenerators like open type feed water heater, sometimes that is called as the aerator, because we can take out certain air bubbles from by mixing those kind of water. And all those kind of feed water heaters need steams. So there are certain lines that are connected in the middle of steam turbines to take a certain amount of steam to mix with cold water after condenser to make up preheating. So those kind of parts are for regeneration. So boiler, multi-stage turbines, and regenerators and condenser. So those are basic kind of components that you can see by looking at the real, actual, big scale steam power plant.